Section 1 Introduction. We're excited to introduce our work in this paper. In recent times, we've seen significant progress in the field of discrete acoustic token modeling, which has greatly improved the autoregressive generation of speech and music. At the same time, techniques using non-autoregressive parallel iterative decoding have been developed for efficient image creation. This method of decoding is faster than autoregressive methods and is particularly useful for tasks like infill, which need to consider both past and future sequence elements. In our research, we've combined parallel iterative decoding with acoustic token modeling and applied it to the synthesis of music audio. As far as we know, we're the first to extend parallel iterative decoding to the generation of neural audio music. During the peer review of our work, Google released Soundstorm, which uses a similar approach to ours. We've developed a model, which we've named VampNet, that can be adapted for various applications through token-based prompting. We've demonstrated that we can direct VampNet's generation by selectively masking music token sequences, essentially asking it to fill in the gaps. The results of this process can range from a high-quality audio compression technique to variations on the original input music that maintain the style, genre, beat, and instrumentation of the original, while altering specifics of timbre and rhythm. Unlike autoregressive music models, which can only continue music using some prefix audio as a prompt and generate music that could plausibly follow it, our approach allows the prompts to be placed anywhere. We've experimented with a variety of prompt designs, including periodic, compression, and musically informed ones, for example, masking on the beat. We've found that our model responds well to prompts to create loops and variations, hence the name VampNet. The term vamp refers to the repetition of a short passage of music with variation. We've made our code open source and we strongly encourage readers to listen to our audio samples. Section Summary. In this section, the authors introduce their work on combining parallel iterative decoding with acoustic token modeling for music audio synthesis. Their model, called VampNet, allows for flexible application through token-based prompting, enabling tasks like infill and variations on the original input music. Unlike autoregressive models, VampNet allows prompts to be placed anywhere and responds well to prompts for loops and variations. The authors provide open source code and audio samples for further exploration. Section 2 Background. We'll start by discussing the background of our study. We've been focusing on two-stage generative modeling, which has become quite popular in the fields of image and audio synthesis, mainly due to its computational efficiency. In the first stage, we learn a set of discrete tokens that are specific to the domain we're interested in. We achieve this by running the input through an encoder, which gives us these tokens. These tokens can then be converted back into the original input domain using a corresponding decoder. In the second stage, we train a model to generate these tokens. We can optionally provide some conditioning to this model, such as previous tokens, a text description, or a class label, to guide the generation process. Now, let's talk about the first stage, which is tokenization. In the field of images, visual tokenization has been used to achieve top-notch classification and synthesis. The most common method is to use vector quantization in a latent space. Similar methods have been tried for audio, but until recently, these methods were limited to low sampling rates, for example, 16 kHz, or were only used for speech audio. The sampling rate of the latent space, which refers to the number of latent vectors needed every second to represent audio, is a crucial part of the tokenization scheme. The lower the sampling rate of the latent space, the easier it will be to accomplish the next stage, which is generation. Recently, methods based on residual vector quantization have been proposed for audio tokenization. These methods allow for high compression rates and good reconstruction quality of high sample rate audio. The main method we use for audio tokenization is the Descript Audio Codec, DAC. With DAC, audio is encoded into a sequence of tokens using a fully convolutional encoder. The output of this encoder is then quantized using a hierarchical sequence of vector quantizers. Each quantizer works on the residual error of the quantizer before it. Thanks to this residual vector quantization, DAC can reconstruct audio with very high quality, at a high compression ratio. DAC, along with its predecessors, have been key in enabling audio language models like Audio LM, Music LM, and Vol-E. While we will briefly describe our tokenizer later, the main contributions of our work can be applied to the output of any audio tokenizer. Therefore, our specific audio tokenizer is not the main focus of this work. Section Summary. Two-stage generative modeling approaches have become popular in image and audio synthesis due to their computational efficiency. In the first stage, a discrete set of tokens is learned for the domain of interest, which can be converted back into the input domain. In the second stage, a model is trained to generate tokens, optionally guided by conditioning factors. Tokenization schemes with lower sampling rates in the latent space have been found to facilitate easier generation, and recent methods based on residual vector quantization have shown promise in audio tokenization at high compression rates. Section 2.2 Stage 2 Generation. In the second stage of our process, we generate audio from encoded tokens. The typical method for this is to use a model that generates each token one after the other, a process known as autoregressive modeling. This is the approach used by leading audio generation models like Audio LM, Music LM, and Jukebox. However, this method is slow due to the large number of steps needed during the inference phase. Moreover, it limits the applications of the model because each token generated is only based on the previous ones. For instance, if we want the model to fill in missing parts, we need to rearrange the data during training. In language processing, a technique called masked modeling is often used to train models to understand semantics. This technique has also been applied to images and audio. In masked modeling, a certain percentage of tokens are hidden during training. For instance, in the BERT model, 15% of tokens are masked. This method is similar to a single-step discrete diffusion model that uses masking as a noise procedure. We can adapt this method for generative modeling by changing the probability of masking a token during training. This approach has been used in image generation and language processing. Like diffusion modeling, which creates data from random noise through a series of denoising steps, masked generative modeling creates data from fully masked data through a series of unmasking steps. The efficiency of this method relies on a parallel iterative decoding procedure. In this procedure, the model predicts every token in the output sequence in one go. However, the output quality is often low after just one pass of the model. To improve this, the output of the first sampling step is remasked with a lower masking probability and then put through the model again. This allows the model to refine its output efficiently, resulting in high-quality generation. In tasks where the model is asked to generate a realistic sample from scratch without any guidance, the model often struggles due to the complexity of the target data distributions. These models often produce blurry samples or suffer from mode collapse and mode averaging. To help the model, we can provide some guidance or conditioning. This can be in the form of a class label, a genre tag, lyrics, or an associated text description. Conditioning can also be applied at every step, like the semantic tokens of Audio LM, or aligned text or phonemes for text-to-speech generation. In our work, we use a masked generative modeling approach with a parallel iterative decoding procedure, inspired by work in vision such as masked GIT and PAEA. We don't apply any conditioning beyond that provided by the unmasked tokens in our encoded audio. As we'll show later, different masking approaches applied at inference time can be used to guide generation. In creative ways. During training, tokens are randomly masked throughout the sequence. The model is then asked to predict the value of each of the masked tokens in one pass, but it is conditioned on all of the unmasked tokens, both in the future and in the past. We vary the number of tokens that are masked during training, which allows us to generate audio at inference time through a sampling procedure. We'll now describe our method in more detail. Section Summary. The second stage of audio generation involves using an autoregressive model to generate acoustic tokens in a step-by-step manner. However, this approach is slow and limits downstream applications. To overcome this, we can extend the concept of masked modeling, where tokens are masked during training, to masked generative modeling. This allows for efficient refinement of the output and helps address issues such as mode collapse and blurry samples in unconditional generative models. Section 3 Method. We've developed a method that modifies the masked visual token modeling process, originally proposed in masked GIT, to suit the audio domain. We've named our approach Masked Acoustic Token Modeling. In our method, we first train an audio tokenizer using techniques from DAC. Unlike the visual tokens in masked GIT, our acoustic tokens are hierarchical due to the use of residual vector quantization. To start, we encode the audio signal at each time step as a d-dimensional latent vector, z. We then divide z into n parts using vector quantizers. The first quantizer produces an approximation of z, which we denote as z-hat1, and a residual error, r1. The residual from each quantizer is then passed to the next one, which produces an approximation of the remaining residual error. We reconstruct z by adding up the output of all the n quantizers. Since the encoded signal is represented as a quantized vector of n discrete tokens at each time step, we have n tokens that can be masked or unmasked at each time step. Instead of trying to generate all tokens at once, we divide the n tokens into coarse and fine tokens. We then train two generative models, one that generates the fine tokens using the coarse tokens as a guide, and one that generates the coarse tokens using a sequence of coarse tokens. To generate a sample, we first use the coarse model to generate a sequence of coarse tokens. Then, we use the coarse to fine model to generate the fine tokens. We convert the tokens into a 44.1 kHz waveform using the decoder of our audio tokenizer. For the training procedure, we use a matrix, Y, to represent the output of the encoder for an audio segment. Each element in Y is a token from the nth level codebook at time step t. We denote the set of all masked tokens in Y as Ym and the set of all unmasked tokens in Y as Yu. The model generates a probability distribution over the set of possible codebook values for each token in Ym, given the unmasked tokens and the model parameters. The training objective is to maximize the probability of the true tokens, which is equivalent to minimizing the negative log likelihood. To predict the masked tokens, we use a multi-layer bidirectional transformer, which predicts the probabilities of each possible token at every time step, for every quantizer. If each quantizer has a codebook size of C possible values, and there are n quantizers, then the last layer of the network will be a fully connected layer of shape, E, Cn, where E is the dimensionality of the output of the last layer. We then reshape this output into N, C, and compute the cross-entropy loss between the ground truth 1 hot token and the predicted token. Because the transformer is bidirectional, it can attend to all tokens in the input sequence to optimize the loss for each token. For the coarse-to-fine generative model, the input sequence always contains NC coarse tokens, and the masking operation is restricted to the NF fine tokens. The last layer of this network only predicts masked fine tokens. The training procedure for both models is identical otherwise. Section summary. In this section, the authors introduce a method called masked acoustic token modeling, which is an adaptation of masked visual token modeling for audio. They describe the process of training an audio tokenizer and encoding the audio signal into a hierarchical latent vector. They also explain the generation of coarse and fine tokens, and the training procedure for predicting masked tokens using a bidirectional transformer. Section 3.3 Sampling. Section summary. The sampling process in VampNet follows an iterative confidence-based approach, where masked tokens are estimated and sampled from a conditional probability distribution. These sampled tokens are then ranked based on their confidence, and a certain number of low-confidence estimates are discarded and remasked. The process is repeated until the desired number of iterations is reached. Additionally, VampNet allows for interactive music editing by incorporating human guidance through various types of prompts, such as prefix and suffix audio, periodic prompts, compression prompts, and music-specific prompts, which can be combined to create a versatile music creation tool. Section 4 Experiments. In this section, we'll discuss the experiments we conducted to assess the ability of VampNet to both compress and generate music, using the various prompting strategies we've previously described. To measure the quality of the audio objectively, we used two metrics, a multi-scale Mel reconstruction error and the Fréchet audio distance, FAD. The Mel reconstruction error is calculated by comparing the log Mel spectrograms at different timescales. In simpler terms, it's like measuring the difference between the original and the compressed version of the music. However, this metric is more useful for evaluating compression quality rather than generation quality, as it's expected that the generated audio won't exactly match the original. For assessing the quality of the generated music, we used the FAD. This metric measures how much the distributions of the real and generated audio overlap. Unlike the Mel reconstruction error, FAD is more suitable for evaluating whether the quality of the generated samples falls within the range of the real audio data. For our experiments, we gathered a large dataset of popular music recordings, similar to the Jukebox project. Our dataset includes 797,000 tracks, all sampled at a rate of 32 kHz. We then resampled these tracks to 44.1 kHz to make them compatible with our tokenizer. The dataset spans a wide range of genres and includes music from thousands of artists. We also ensured that there was no overlap of artists between the training, validation, and testing tracks. Additionally, we collected a set of music and non-music data, which we used to train our tokenizer. The audio tokenizer model we used takes 44.1 kHz audio as input and compresses it to a bitrate of 8 kilobits per second using 14 codebooks. The resulting latent space is at 57 Hz, with 14 tokens to predict at every time step. We trained the tokenizer for 250,000 steps. The architecture of VampNet consists of a bidirectional transformer with relative attention. The model has an embedding dimension of 1280 and 20 attention heads. We trained the model for 1 million steps for the coarse model and 500,000 steps for the coarse to fine model. We used the Atom W optimizer with specific settings for the learning rate and warm-up steps. We also used a dropout of 0.1 and a batch size of 25, with a GPU memory budget of 72 GB. Section Summary. The experiments conducted aimed to assess the ability of VampNet to both compress and generate music using different prompting strategies. For compression quality, the MEL reconstruction error was measured, which compares the log-MEL spectrograms of the original and generated audio. For generation quality, the Fréchet audio distance, FAD, was used to evaluate the overlap between distributions of real and generated audio. The dataset used consisted of 797K tracks of popular music, with subsets of 2K tracks for validation and testing. The network architecture involved a bidirectional transformer with relative attention and an embedding dimension of 1280 and 20 attention heads. The models were trained using the Atom W optimizer with specific hyperparameters. Section 4.3 Efficiency of VampNet. In this section, we'll first discuss the efficiency of VampNet, our music generation model. We want to confirm that VampNet can create realistic music audio quickly. To test this, we use one of our prompts, the periodic prompt, with a cycle of 16, on our test set, specifically on 10-second music clips. We experiment with different numbers of sampling steps, ranging from 1 to 72, and record the results for each step. Next, we explore how VampNet reacts to different prompts, as we've previously discussed. These prompts vary from compression prompts, which reduce music to a low bitrate, to more creative, generative prompts. We're interested in whether there's a spectrum between compression and generative prompts, and if decompressing from low bitrates leads to generative behavior. To investigate this, we take 2010-second music clips from our evaluation dataset, convert them into token streams using our audio tokenizer, and then manipulate these token streams in 4 ways. 1. Compression prompt. We leave only the C codebooks unmasked, starting from the coarsest one. All other tokens are masked. We set the number of codebooks, n_k, to 1. 2. Periodic prompt. Every pth timestep is left unmasked. In an unmasked timestep, tokens from every codebook are unmasked. All other tokens, for example, tokens in timesteps that don't match the period p, are masked. We set p to be either 8, 16, or 32. 3. Prefix and suffix, inpaint, prompts. We leave a segment at the start and end of the sequence unmasked. All other tokens are masked. This prompt is defined by context length in seconds. We set the context to be either 1 second or 2 seconds, which corresponds to 57 or 114 time steps. 4. Beat-driven prompt. We first process the audio waveform with a beat tracker. Then, around each detected beat, we unmask time steps to the right of the beat. We examine a 75 milliseconds unmasked section around each beat, which is about 4 time steps per beat. After manipulating the input token streams with our prompts, we use VampNet to generate new music from these masked token streams. We then calculate the FAD and MEL reconstruction error between the generated music and the original music from our dataset. We also include a noisy token stream baseline, where a portion, as determined by mask ratio R, of the tokens in the input token stream are replaced with random tokens. We also use the codec by itself and the coarse-to-fine model as baselines. Lastly, we look at how these prompts can be combined, specifically the compression and periodic prompts. By adjusting the hyperparameters of these prompts, C and P, we can shift the model behavior from compression to generation. As more time steps are masked, the model must generate plausible music clips that connect the unmasked time steps, which may not match the original music. Section Summary. In this section, the authors validate the efficiency of VampNet in generating realistic music audio with a low number of steps. They vary the number of sampling steps and report metrics for each step. They also explore the effect of different prompts on VampNet's response, ranging from compression prompts to generative prompts, and examine how prompts can be combined to shift the model behavior from compression to generation. Section 5 Results and Discussion. In our study, we experimented with the number of sampling steps used to generate samples with VampNet. The results, as shown in the figure, indicate that VampNet performs best with 36 sampling steps, although 12 steps also yield similar results. However, we found that 24 steps provide a good balance between the quality of the generated samples and the speed of computation. For instance, it takes about 6 seconds to generate a 10-second sample on an NVIDIA RTX 3090. In comparison, an autoregressive model would require 574 steps to generate a 10-second audio, which would take approximately 1 minute. We also studied the impact of each prompt. The results, depicted in the figure, show that while the noisy token baseline has a similar MEL reconstruction to all prompts, it performs poorly in terms of FAD. This suggests that our prompting strategies may not perfectly match the original input audio, but they still produce plausible music. Among our proposed prompts, the beat-driven ones perform the best, achieving the lowest FAD. Interestingly, the periodic prompt with P equals 16, 35 conditioning time steps, performs as well as inpainting with 1 second of context, 57 conditioning time steps. This suggests that prompts that distribute the conditioning tokens throughout the sequence, periodic prompts, can generate samples of similar quality to those generated by techniques that place all the conditioning tokens at the start and end of the sequences, inpainting, but with fewer conditioning time steps. In terms of quality, we found that beat-driven prompts maintain a more consistent tempo than other prompts, although their outputs tend to be more similar to the original music than periodic prompts. In practice, a combination of beat-driven, periodic, and inpainting prompts can be used to guide VampNet creatively. We encourage readers to listen to the accompanying audio samples for a better understanding. We also combine periodic and compression prompting to observe how the model's behavior changes between reconstruction and generation tasks as more tokens are masked away. The results, shown in the figure, indicate that at higher bitrates, 600 bits per second and above, VampNet can accurately reconstruct the original music signal, achieving low MEL spectrogram error and FAD values. However, at bitrates of 200 bits per second and below, VampNet's reconstruction quality is similar to the noisy token baselines, suggesting that the sampled VampNet signals no longer resemble the input audio in terms of fine-grained spectral structure. Despite this, the FAD for VampNet samples at low bitrates is much lower than the FAD for noisy baselines. This suggests that even though VampNet can't reconstruct the input music signal at low bitrates, it can still generate coherent audio signals with musical structure that are closer to real music than our noisy baseline. Section summary. The results of our experiment show that VampNet achieves the lowest FAD, fretchet audio distance, with 36 sampling steps, but comparable performance can be achieved with 12 sampling steps. Samples taken with 24 steps strike a good balance between generation quality and compute speed. Additionally, beat-driven prompts perform the best in terms of FAD, while periodic prompts with fewer conditioning time steps perform on par with inpainting prompts. A combination of beat-driven, periodic, and inpainting prompts can be used to steer VampNet creatively. At low bitrates, VampNet is not able to accurately reconstruct the input audio but can generate coherent audio signals with musical structure that are closer to the distribution of real music than the noisy baseline.